Here you can use an operational amplifier to act as a differentiator. That is, it'll take the input signal or the input voltage and differentiate it. Okay, the circuit for that looks something like this. Capacitor connected to a voltage source. We feed back the output through a resistor through the non-inverting input, and then the non-inverting input is grounded. Okay, so let's see how this circuit would act as a differentiator. So what we're trying to do is we're trying to express V out as a function of V input. Now it will not be that it will be like V out divided by V in, because there is going to be some differentiating action. So the claim is that this F will actually be, I think it'll be a derivative. So how does it act to be a derivative? That's a derivation we'll just do. So we make a copy. Okay, so we'll proceed exactly like what we've done before. No changes. Let's assume that there is a current. Okay, so now there's a problem. This will actually not, capacitor won't really allow a current to flow, right? It will only allow a charge to flow. So what we can do is we can write this as I in as dq in dt, where q is the charge flowing and the derivative of the charge is the current. And then we have I out. And then the usual things about this. This is V minus, V positive. Okay, that's it. So let's analyze this. Nothing different from what we did so far. Let's take this. Let's take this point as, so now I can call it C because I already have C there. So let me call that A. And let me try to set up the equations now. Okay, so we can try to compute the voltage drop across the resistor R. That would be V out minus VA equals I out R. Okay, we can also write perhaps a relation for the charge flowing across the capacitor. Okay, so V in is the potential here, and VA is the potential at the other end of the capacitor. So the voltage drop across the capacitor is going to be V in minus VA equals Q in. It's C times V, right? So it's going to be Q divided by C. Okay. Okay, now there's a simplifying thing we can do here, which is from the assumptions of our Opamp, we know that V minus is V plus, but V plus is 0. Because V plus is connected to the ground. We also know that VA is nothing but connected to the negative end or the inverting end. So VA should be equal to V minus. And so from all these, we can see that VA should be 0 because it's from here. Okay, so we can just get rid of this. Now, what you see is that we have I out, we have Q in, and those two are the unknowns here. So the way to deal with the unknowns is using KCL. Let's try to see if we can relate I out with I in or Q in. So we can see that at A, the currents going inside A are I out plus I in, right? Equals 0 because the current coming out, I minus, over here is 0. No current flows in an op-amp because the high input impedance. Okay, so I think with all this information, we are set to simplify this. Let's just take this. Okay, from this, let's write I out as negative I in, but I in is dq I in dt. Okay, let's just call this a 1 and 2. So what I'm going to do is I'm just going to replace the value of I out and Q in from 1 and 2. So from 1 and 2, we have P out divided by R. This is the part which I replaced from equation 1. Equals minus d dt of Q in, but Q in is C times V in. This is the substitute for Q in from 1. This is from 2, and this is from 1. So V out divided by R is minus. So C the constant, C d V in dt. And so we see that the output voltage is minus RC dV in dt. Okay, so the output voltage is actually a derivative of the input with a negative sign. So where could this be used? Well, if your input is, let's say, a sensor which gives you position, then your output is going to be the derivative of the position. So it will give you the velocity. So this is a way in which you can use an operational amplifier to do computations by itself. You don't really have to write any code, right? There's no code here. There's just this machinery, the Opamp machinery, which gives you the right output depending on how you wire it up. Yeah, there's another Opamp which can do integration. I will draw the circuit diagram for you, and then I'm expecting that you will analyze this at home. Okay, similar ways which I did here in class. So here is number 4th circuit, an integrator. Okay, an Opamp. Capacitor fed back to the Inverting input goes through a resistor, connects to a voltage source, to the ground, and then the non-inverting is connected to the ground. This is R, this is C. So your task to do is you need to show that V out is -1 divided by RC, integral 0 to T, P in tau theta. Okay, so show that at home. Okay, so again, one use of this would be if you have, let's see, what sensor gives you a derivative? A velocimeter. I don't know if you know about that. It's basically a sensor which measures linear velocity, not angular, or even a gyroscope is more common. Gyroscope is a sensor which gives you angular speed. So if you take that angular speed as an input, provide it to this circuit in Opamp, it will integrate and give you some estimate of the angle. It needs to be zeroed though.